So now you have the pieces you need to construct our very first climate model of a naked planet. So we have sunlight that's coming from the sun and coming all in one direction toward the Earth. And then we have Earth that is shining its own light based on its own temperature with light that's going in all different directions around the surface of the Earth. And what we're doing to solve for the temperature of the Earth is we're solving for the condition where the energy coming into the planet balances the energy that's leaving. That's the eventual steady state. And an analogy to that would be if we had a kitchen sink and you turn on the faucet and the water starts to build up in the sink and it gets deeper and deeper, and as it gets deeper in the sink, there's more pressure of water pushing it down the drain. And so the rate at which the water leaves the sink is a function of how deep the water is in the sink. And so the water level in the sink, if it starts out all the way down, will rise until it comes close to the level at which the water budget balances and stay there. Or if you start out with too much water, it'll sink until it goes to that steady state value and stay there. So the water, if this is the rate of water flow in from the faucet, and you started out with no water, there'd be no more coming in than out initially, and so the water would build up and it would tend to relax to that condition of balance. Or if you walk up to it with a big bucket and dump a big bucket all at once in there, you'd start out with too much water and it would relax downward toward that steady state value. So what we were doing in this calculation is going right for that steady state value. So we're looking for the condition where the energy in is equal to the energy out. And so we'll look at this in pieces. The energy going out, you now know, is given by the Stefan Boltzmann formula, epsilon sigma temperature to the fourth, where the temperature is the temperature of the Earth, and we're assuming for now that it's all the same temperature because it's a very, very simple model. Epsilon for the Earth is pretty close to 1. Most solids and liquids, most condensed matter has pretty good black-body properties, and so it has epsilon pretty close to 1. The exception to that we'll get to is greenhouse gases, a very important exception. But for now, we can kind of just call that 1 and not worry about it, and this is Stefan Boltzmann constant, which you can just look up in a book. So this tells us the energy flux in watts per square meter. But if we want to do the planet overall, we have to multiply by the area of the surface of that sphere. So this area, to get rid of the watts per square meter, and the area of a sphere is 4 pi r squared. Now, on the other side of the equation, we have the energy coming in from the sun, and this is given by a solar constant, which is a number in watts per square meter, which is determined by how bright the sun is, but also how far away we are from the sun. So it's how bright the sunshine is. If you look at it, straight on at the distance from the sun to the Earth, it's about 1,350 watts per square meter of area. So if you had a solar cell 1 square meter in size, you could about run a normal sort of hairdryer on that. That's kind of the energy flux coming through that. But not all of that energy actually is absorbed as heat by the planet. Some of it gets reflected back out to space and never gets absorbed. And that fraction is reflected in the albedo, which is given the Greek letter alpha. So 1 minus albedo is the fraction that gets absorbed. The value of the albedo for the Earth is about 30% because of the clouds mostly reflecting light back out to space. And then, so this is in watts per square meter, but it's in per square meter of this energy, that's coming from the sun, sort of looking straight on. And we have to multiply it by an area to get just the total energy coming in. But this is a bit trickier now because the area of the Earth isn't all facing directly at the sun, perpendicular to the way the sun is coming. So we could do a complicated integral where we add up all the square meters of the Earth and figure out which ones are sort of oblique, and so they're not getting as intense sunlight. But there's a tricky, easier way to do it, and that is to realize that the amount of light that is intercepted by this planet is given by the size of the shadow of the Earth. And that shadow is all directly straight on to the sun, and so it's oriented in the right way. And so this area now is not the area of the sphere that we had before, but it's the area of a circle, which is only pi r squared. So if we equate those two sides, we have the solar constant times the fraction that's absorbed times the area of the shadow, and here's the infrared emission, the black body radiation, and the area of the sphere. But we can now divide by pi r squared. In fact, we can even divide by 4 pi r squared to get this equation, which is in the most convenient form. It's now in units of watts per square meter of the surface of the sphere, so per square meter of the Earth's surface. So what we have now is an equation that only has one unknown in it, and that's the temperature of the planet. And so we can rearrange that and calculate what the temperature should be for any given combination of the solar constant and the albedo. So this is a table of how that calculation goes for the Earth and our sister planets, Venus and Mars. The solar constant is much higher for Venus because Venus is closer to the Earth than the Earth is, and it's lower for Mars. That's because the intensity goes down as you get further from the source. The reflectivity of Venus is very, very high. That's because Venus is covered with clouds all the time. Venus is the second brightest thing in the night sky. And it's not because Venus is so hot that it's shining red light, it's not or white light, it's not a star. It's just reflecting the light that's coming in from the sun because of these clouds. And then Mars doesn't really have clouds or much of any ice, and so it's mostly sort of darkish rock, and so it has a fairly low albedo. So here is where we calculate the temperature of these planets given their solar constant and albedo values. And it's interesting, Venus, because it's so reflective, would be even colder than the Earth, even though it's closer to the sun. It's just wasting all that energy by reflecting it out to space. And then the Earth is warmer than Venus, and then Mars is cool again because it's so far from the sun. But the real interesting thing comes when we compare with the real temperatures that the planets actually have. Venus is much, much hotter than we just predicted. Earth is hotter than we predicted, and so is Mars. They are all, the climate model, as we've done it so far, is always too cold. So our first climate model was too cold, and the remedy to that is to add the greenhouse effect. And we're going to do that in a way that's very, very simple. You wouldn't understand the greenhouse effect without understanding this simple model that I'm going to show you. But of course, reality is much more complicated. So after we put together this very simple model and understand it, we'll be spending a fair bit of time in the class actually talking about how to make it more realistic, to make it more like the real world. So the bare Earth model that we looked at last time was basically this. It had sunlight coming in and energy leaving according to epsilon sigma temperature of the ground to the 4th power. So our new model with the greenhouse effect, we're going to suspend a pane of glass above the ground. And the glass has the property that sunlight can go through it without any impediment. It's not absorbed by the glass. But any infrared that comes from the ground is going to be absorbed by that pane of glass. And the glass itself is going to shine in the infrared in both directions, up and down, according to its own temperature, the temperature of the pane of glass, or as I've written, the atmosphere, the temperature of the atmosphere here. So we're assuming throughout all of this that these epsilon values are equal to 1. So that means that the glass has all of the oscillators that it needs to make a nice smooth black body curve and create the full sigma t to the 4th black body spectrum. Of course, it's not a perfect black body, because if it were, it would absorb the sunlight too. According to the definition, it should absorb and emit all frequencies. So it's kind of a selective infrared kind of a black body. And we're going to solve for the equilibrium temperature such that the energy is in steady state, just like we did before. We're going to look for the energy in and equate that to the energy going out. And there are multiple places where we can construct a budget in this new model, because there's actually multiple temperatures. There's the temperature of the ground and the temperature of the atmosphere. So starting from the ground, since we are sort of ground-based beings after all, we can just look at the arrows going into and coming out of the ground and write them as inputs and outputs. So what's coming into the ground here, we've got the same sunlight as before, and we have this arrow of infrared coming down from the sky. And so that's epsilon sigma temperature of atmosphere to the 4th power. That's what's coming in. And then what's going out of the ground is just sigma T temperature of the ground to the 4th power there. So that's not really as convenient as the last equation we looked at, because we have 2 unknowns in it. We can't solve for both of them at the same time with just one equation. If you want to solve for 2 unknowns, you need 2 constraints, 2 equations. So here's another one. This is the budget for the pane of glass. So we have what comes into the pane of glass is not the solar energy at all. It is, in fact, the epsilon sigma temperature of the ground to the 4th power. That's this arrow coming into the glass there. And then what's leaving the pane of glass is epsilon sigma temperature of the pane of glass to the 4th power. And there's this factor of 2, because the light is going both upward and downward. This 2 is not the most intuitive thing. You wouldn't probably have thought of it. But without that factor of 2 there actually wouldn't be a greenhouse effect, as we'll see. So this is now an equation that has 2 unknowns in it, temperature of the ground and the temperature of the atmosphere, rather haphazardly written there. And so we could, in principle, take these 2 equations and use algebraic substitution to solve for just one of the temperatures, and then use that, plug that back in to solve for the other one. And you're welcome to do that if you like to try your algebra chops. But there's an easier way to do it, and it actually has a conceptual benefit as well, that we can draw a different budget. And it is a budget for the Earth system overall. So we can draw a line, sort of a boundary to space above the atmosphere, and the energy crossing this boundary to space coming down has to balance the energy crossing the boundary to space going up. In the steady state, everything has to be in balance. And so if we write those equations, what's coming down is just our familiar sunshine, L times 1 minus the albedo over 4. And then what's going out is epsilon sigma temperature of the atmosphere to the 4th. So this equation should look familiar to you. This is actually the same equation that we got from the last model for the temperature of the ground. Only now it's at the temperature of the upper layer. And it turns out this is sort of a general property of these simple models and also of the more complicated Earth system, that the temperature where the energy shines out to space is kind of a fulcrum point. It's fixed by how bright the sunshine is and how much is reflected away in the albedo. So this is the naked Earth model, and the temperature of the ground is 255 Kelvin. Here is our greenhouse model with 1 pane of glass here, and the temperature of the pane of glass is 255 Kelvin again. In the exercises, you're going to work out the balance of this super greenhouse model that has 2 panes of glass, so twice as much greenhouse forcing as that. And what you will find is that the top layer is 255 Kelvin. And you'll also work out a nuclear winter scenario where there's crud in the atmosphere, and so the sunlight gets absorbed in the atmosphere. It doesn't go down to the ground. And it turns out that has a big impact on the temperature of the ground, but it has no impact on the top layer, which is, again, still 255 Kelvin. So it's this very useful conceptual thing to keep in mind. And it's also algebraically much simpler to solve, because once you have the top temperature here, you can take the budget for the atmosphere here and very easily solve for the temperature of the ground given this temperature of the atmosphere. It turns out the temperature of the ground is equal to the temperature of the atmosphere times this factor of the fourth root of 2, which is about 1.189, so about 20% warmer. So what's happening is that in our kitchen sink analogy, where the water, was at its steady state level in the sink and enough to drive it down the drain as fast as it's coming in from the faucet, it's as though a little piece of carrot came and got stuck on the drain filter there. And it doesn't plug it up completely, because then the sink would flood and the analogy would blow up and it would be no good for anybody. But it sort of partially obstructs it, and it means that the water has to try harder to get out. And so what happens then is that the water level compensates for that eventually, not instantaneously, but eventually it'll build up to a new equilibrium with a higher water level where the energy fluxes are balancing again. So the water didn't come from a giant bucket full, the carrot didn't come with a bunch of water in it, nor did the pane of glass come with a bunch of energy in it, but it just traps the energy, or the water in this case, and allows it to build up to a newer, higher concentration. So if we come back to our table of the Goldilocks planets here, Venus, Earth, and Mars, here is now the temperature of the one-layer model, the temperature of the ground when you have one pane of glass over it. And in all cases, it's warming up by about 20%, which is that factor of a fourth root of 2. So you can see that for the Earth, this greenhouse effect is a little more powerful than the reality. That's true also for Mars. But for Venus, we need a much more powerful greenhouse effect to build up this 700 degrees Kelvin, which is hot enough to melt lead on Venus. So it's sort of an approximation to the greenhouse effect, but we will learn about the complexities and the things that can make it stronger or weaker as we go on.